Hello and welcome back to my channel. A materials revolution is starting right now. It will redefine industries like semiconductors and quantum technology. NITI Aayog points out that we are on the edge of a massive shift. Imagine a glass of materials so thin that they are only one atom thick. These are called two-dimensional or 2D materials. They are characterized by atomically thin layers and extraordinary electronic, optical, and mechanical properties. They are not just scientific wonders, they can enable entirely new device architectures. They can power faster electronics, flexible devices, and quantum platforms. For India, this rise of 2D materials is a strategic necessity. It requires building indigenous expertise and academic industrial collaboration. The choices we make today will shape our technological sovereignty and global influence for decades to come. Let us look closer at what 2D materials actually are. They are crystalline substances with a thickness of just one to a few atomic layers. This is typically less than 1 nanometer. To put this in perspective, 1 nanometer is 800,000 times smaller than a pencil tip. It is about 1 over 80,000 the width of a human hair. Their unique properties come from a special atomic structure. In materials like graphene, strong covalent bonds hold the atoms together in a tight, flat, honeycomb lattice. This arrangement distributes physical forces evenly, making them extremely strong. It also allows electrons to flow smoothly without hitting defects, which leads to high electron mobility. Furthermore, their thin nature gives them a high surface to volume ratio. This makes them very sensitive to environmental changes. They are perfect for advanced sensors, wearable logic devices, and flexible screens. Graphene was first isolated in 2004 using adhesive tape. It is a single layer of carbon atoms arranged in a hexagonal lattice. It is 200 times stronger than steel and conducts electricity better than copper. However, graphene has a major limitation for digital electronics. It lacks an electronic band gap. This means its electrical flow is always on and cannot be switched off. To solve this, researchers use another class of 2D materials. These are called transition metal dico, di, dichalcogenides or TMDCs. Retake. These are called transition metal dichalcogenides or TMDCs. TMDCs are atomically thin lattices of metal and chalcogen atoms. Unlike graphene, TMDCs have natural electronic band gaps. We can precisely tune these band gaps by changing the number of layers or applying strain. This tunable band gap makes TMDCs perfect for building next generation transistors. They will help push chip scaling beyond traditional silicon. Monolayer 2D materials have pristine, high mobility crystalline structures that are ideal for high tech sectors. In nano-electronics, monolayer TMDCs enable high on and off ratios and low leakage currents. This overcomes the short channel limitations of silicon, allowing transistor scaling into the angstrom regime. In neuromorphic computing, stacked 2D layers exhibit unique memorization switching behavior. These allow researchers to build synaptic transistors that mimic human brain functions. These materials also excel in optoelectronics. They have strong light matter interactions and tunable band gaps, which are perfect for ultra thin photodetectors and spectral imaging. For quantum computing, monolayer TMDCs exhibit strong spin valley coupling. This unique feature allows encoding information in valley and spin indices. It also helps confine carriers in tiny quantum dots to host robust quantum or qubits. All of these advanced features can also be directly integrated onto flexible substrates. We must distinguish monolayer crystals from bulk, polycrystalline, and ink based 2D materials. Bulk forms include graphene oxide, reduced graphene oxides, and functionalized composites. These are used for their mechanical strength, thermal stability, and surface chemical activity rather than logic functions. When mixed into polymers or metals, they dramatically improve tensile strength and reduce weight. This makes them ideal for aerospace structures, sporting gear, and concrete. In energy storage, reduced graphene oxide and TMDCs flakes serve as battery electrodes. Their high surface area provides efficient pathways for rapid charging in electric vehicles. Environmental technologies also benefit greatly. Graphene oxide membranes have nanoscale channels. These channels act as selective molecular sieves. They filter out salts, heavy metals, and organic pollutants for water purification. They are also being developed for carbon capture systems. The semiconductor industry is now a critical axis of national security and geopolitics. Both the United States and the European Union have enacted major CHIPS Acts to boost onshore production. The US CHIPS Act provides $39 billion in direct grants and 25% tax credits. The EU CHIPS Act mobilizes 43 billion euros to ensure European strategic autonomy. This is because advanced chip fabrication is heavily concentrated in Taiwan. A disruption there would cost the global economy an estimated $10 trillion. 2D materials are deeply tied to this high stakes global chessboard. Their supply chain is highly vulnerable. For example, the technology depends on advanced foundries, precision metrology, and high purity precursors controlled by a few nations. Recent export controls on essential materials like graphite and gallium highlight the urgent need for national self reliance. Western countries are actively advocating for supply chain resilience. They are doing this through a strategy called friendshoring. This means moving production away from potentially hostile nations to trusted partners. Economic data indicates that global investment trends are shifting. Large multinational firms, including Apple, are moving production to Vietnam and India. Research shows that if the West friendshore its import demand, millions of jobs will relocate. India is positioned as a primary winner in this geo-economic realignment. Its massive labor force, low wages, and improving infrastructures make it highly attractive. Experts project that India can absorb 4.5 million low tech jobs and 6.1 million medium tech jobs from this transition. This shift is expected to occur in a non-linear way like a catch-up bottle effect. Once new supply ecosystems are established, the movement of manufacturing will accelerate rapidly. India has made massive strides in establishing its semiconductor ecosystem. In December 2001, the government launched India's Semiconductor Mission 1.0 with a 76,000 crore incentive framework. It offers up to 50% fiscal support for silicon fabs and packaging units. As of December 2025, 10 projects worth 1.60 lakh crore have been approved across 6 states. These projects are turning India into a global hardware player. For instance, Micron is building a 22,516 crore assembly and testing facility in Gujarat. Tata Electronics is setting up a mega silicon fab in Gujarat with PSMC Taiwan, investigating 91,526 crore. Tata is also building a 27,120 crore packaging plant in Assam. Other approved facilities include CG Power, Kainis Technologies, Vama Sundari, 3D Glass Solutions, 6SAM, CDIL, and ASAP Technologies. These projects will meet critical needs. Building on success of ISM 1.0, the government announced India's Semiconductor Mission 2.0. The Union Budget 2026 to 2027 allocated 1,000 crore for ISM 2.0. This next phase focuses on the producing semiconductor equipment and precursor materials within India. It also emphasizes designing full stack Indian semiconductor intellectual property. While ISM 1.0 built the foundation, ISM 2.0 targets advanced manufacturing. It establishes a clear roadmap to achieve 3 nanometer and 2 nanometer technology nodes. The timing of this mission is perfect. India's domestic semiconductor market was valued at $38 billion in 2023. It is projected to grow rapidly to reach $100 to $110 billion by 2030. By 2029, India aims to manufacture 70 to 75% of its domestic chip requirements. This will ensure deep self reliance. A primary milestone is the launch of the Roof 64. This is a fully indigenous 64-bit microprocessor designed by CDAC under the Microprocessor Development Program. Roof 64 is built on modern architectural principles to deliver high multitasking efficiency. It will be deployed in 5G infrastructure, automotive systems, and IoT devices. This homegrown chip is extremely important. India currently consumes nearly 20% of the global microprocessor output. Group 64 joins a robust family of Indian processors like Shakti, Ajit, Vikram, and Tejas. These are developed under the Digital India RISC-V or DR or DIR-V program. By using open source architecture, India eliminates heavy licensing fees. This allows local startups and universities to collaborate freely and build custom chips indigenously. The rise of 2D materials presents an open but rapidly narrowing window of opportunity. We cannot afford to remain passive. If India fails to invest in 2D materials, its electronics sector risks being locked into low value legacy silicon nodes. We would become permanently dependent on foreign controlled AI chips and quantum platforms. To prevent this, NITI Aayog urges India to transition to a coordinated mission mode 2D material strategy. We must establish national innovation hubs focusing on semiconductors, energy storage, and chemical technologies. Prototyping must move from the lab to wafer scale foundry integration. We must also forge strategic collaborations with international hubs like IMEC and the Graphene flagship. By integrating 2D research directly with the India Semiconductor Mission and the National Quantum Mission, India can score its deep tech industrial future. Thank you very much.